Hello, Physics 2B. Welcome to Week 3, Lecture B, for our coverage of voltage. A big thing about today will be connecting electric fields and voltage, because those are two properties that are most interrelated. There'll be minimal connections between voltage and potential energy made as well. A large part of the first few minutes of this, the first few slides of this, is calling back to previous material. Specifically, back when electric fields were introduced, I made the distinction between what is an electric field and what is a map. And the big difference we have here is that a field has to do with vector quantities, but a map has to do with scalar quantities. That's the big distinction. An example of this is a topographical map. So here we could see the different heights for a mountain, either with the side view down here, or from the overhead view up here. Either way, what we're looking at is our representations of the heights. For the side view one, it's the profile of a mountain that should be, or a pair of hills, which should be rather familiar. But the other one, the topographical map, focuses on the ideas of looking at very specific heights, so that everything associated with this line here is at 30 meters of elevation. Okay, so that every line here, every point on this line is at 30 meters of elevation. And the same for the one over here. This is a topographical map, and this is a common way that voltages are represented. We can show voltages in the same way as we show heights, because mathematically they have a lot of parallels. Physics-wise, they have some important distinctions, like one's about being a distance from an object and one's a voltage, which is an electric quantity. But we will be using both visualizations. Equipotentials, like the topographic map, and profiles of the potentials, like we see in the side view. Okay. We went over electric potential energy earlier this week. In there, we could make our connections between work and forces and potential energy, and furthermore make our connections between forces and electric fields and potential energy. Or we can just say, oh, I'm just dealing with a pair of point charges. Okay, so we have so many perspectives that we could look at these things at. And I do have that broken down more explicitly in the PDF book, if you need that really itemized, approximately page 15 or so. I'm not sure exactly, but it's about page 15, maybe 16. Okay. Let's start with the easiest one. Okay. I want to be able to connect voltages to potential energy. Okay. Voltages are connected to potential energy. Okay. Voltages are to potential energy in the same way as electric fields are to electric forces. All right. suddenly this became an SAT exam. What's going on with this simile? Well, the electric field is defined. There we go. The electric field is defined as the electric force divided by some test charge. That way there's a clear distinction between the interaction and the source that's creating some effect in the region. Voltages act the same way. Voltages are the potential energy per charge. So that we can move it away from talking about an interaction, because potential energy and forces are always interactions, which is why you'll see potential energy of two charges by each other, the force between two charges, an interaction. Whereas voltages and electric fields are due to sources. All right. So to make it just about the source, we divide away the secondary charge and call that a test charge that we'll bring back later as need be. And that's what we're doing here. We're dividing away that charge, making this a voltage instead of potential energy. As such, we can make connections between voltage and electric field, or we can make connections between voltages and point charges. Like that blue star that I have up there, that's where I'm focused first, looking at the voltages near point charges. Let's graph it out. Let's graph it out in a side view. I want to look at the voltage at different positions near different charges. So I'm going to say at this location here, I've got a positive charge. That positive charge, according to V is equal to KQ over R, is only going to make positive voltages, because we've got a positive Q, positive K, positive R, always positive. And with that 1 over R relationship, it's going to drop off like a hyperbola on both sides. Like so for that voltage, and like so for this voltage on the other side. Next, so that's the voltage near a positive charge. Next is going to be a voltage near a negative charge. Again, voltage versus position. Got a negative charge at this location in blue. And voltage is equal to KQ over R. K is positive, R is positive, but Q is negative. As such, this will only create negative voltages, and it'll be in the shape of a hyperbola on both sides. So really we're looking at a mirror image of what we had for the voltages for the positive charge. Mirror image. Next, let's put two charges in the region. Well, if I have two positive charges, I'm going to have a red positive charge here, and I'm going to have a blue positive charge here. The red charge is going to create a voltage like this in the region. The blue charge is going to create a voltage like this in the region. But if I put a third charge in there that's experiencing these voltages, it doesn't care what they are individually for the V1 and for V2. It cares what they are as a total. So bumping this up a little bit, the total voltage in this situation as a function of position, with my red charge being there, my positive blue charge being there, both positive charges. That's going to add up to, let's use purple. On the red side, the red charge is going to dominate, so it's going to look just like the red hyperbola on the left. On the right side, we've got, it's going to be dominated by the blue charge, so it's just going to be like the two on the blue on the right. But in the middle, we've got this addition happening that will add together to create something that looks like a parabola in the middle. Should have made this a little wider. There we go. Cleaning it up a little bit. Cleaner. There we go. And there we have our voltage as at different positions in the region. One more example. On this one more example, I'm going to do something different. Instead of having the horizontal axis be the x-axis, I'm going to have the horizontal axis be the y-axis. Because I want to make a distinction about x direction and y direction. They're both positions that we're talking about. Okay. For the x graph up above, in this direction would be to the right. In this direction would be to the left. But as soon as in my voltage versus, we'll get to voltage total, yeah, versus y, in that case we will have that direction is down and this direction is up. Because positive y direction is up, negative y direction is down. That's a common convention. And it's a convention I try to stick to in the warm-up for today. Okay, so make sure that if you are saying something is left and right, make sure you're really talking about the x direction. And if something is up and down, you're really talking about the y direction. Two charges. The red one is still going to be a positive charge. No surprises there. The blue one is going to be a negative charge. Not too surprising, but it will give a different result. To the left of the positive charge, or rather down from the positive charge, the result from the positive charge will dominate. To the above the negative charge, the negative charge is going to dominate. So it gets a hyperbola like that. Very close to the positive is going to dominate. Very close to the negative is going to dominate. And those voltages are going to meet somewhere in the middle. Okay. And there we have the voltage profile near positive and negative charges. what's the point of these? Let's see, we've got 1, 2, 3, 4 examples here. So what can we get out of these 4 examples? Well, we can learn about the electric field near each of these, which we should already know about because we spent a little time working on it. So looking at, going from the top, the page I was just on, so that the electric field is the negative slope of voltage. And it's a vector, so there's some r hat associated with it, so x hat more specifically. I'm going to do that analysis in green. So here, at this position, there's a positive slope. Seeing as there's a positive slope, the electric field will therefore be in the negative x direction. So like so. Here, there's still a positive slope, but it's a much more positive slope. So the electric field is stronger. And way out here, it's significantly less. And as you get way out here, you end up with an electric field that's basically zero as this voltage levels off, approximately. On the other side, we've got very negative slopes. Where the slope is negative, we end up with the electric field in the positive x direction. And this is going to be a big one, so I'll make sure I draw as big as well. Those are all electric fields in green. Here the slope is significantly less, but in the same direction. And way out here, this is basically flat. So we get an electric field that's basically zero way out there. But it's actually a very small value in the positive x direction. This should not be a surprise, because we expect the electric field to point away from a positive charge. And that's exactly what each of these green arrows does. There's a red positive charge in the middle, and the electric field is pointing outwards from there. Same idea here. We've got a we've got a moderately negative slope there. Negative slope, multiply that by a negative, and I get positive. Therefore, the electric field here will be in the positive x direction. Notice that the electric field is always along the spatial axis. It cannot be in the voltage direction because voltage is not a direction. It's a scalar quantity, not a vector quantity. Symmetrically speaking, I can say that the electric field is going to be inwards there because of the positive slope. I'll end up with a negative electric field. Here, I end up with a very large electric field with this very large slope. Negative slope, positive x hat electric field. And just the opposite on the other side. And much like above, way out here we end up with electric fields of basically zero. Very small, and to the right, and basically zero way out there. Okay. Let's keep it going. This was just used to help us visualize the individual effects and then add them together later. So I'm going to look at the result, because when you have multiple charges, you need to look at the total voltage, not the individual voltages. Okay. Usually at this point I get a question from a student saying, hey, does a zero voltage mean zero electric field? Because it kind of looks like that here. Okay, this thing's tapering off to zero, and so is the electric field. But that's not a valid connection, because it's not about the value of the voltage, it's about the slope of the voltage. Take this location, for example. That location has a positive voltage, but it has a slope of zero. As such, since the slope is zero, the electric field is zero. And all of the electric fields will be downhill. Downhill. Very downhill. Very downhill. Extremely downhill. Extremely downhill. Okay? That's the other way I describe this. Not so much as the negative slope as much, but instead I can say it more colloquially. The electric field points downhill. As long as I remember two things about downhill. One, I mean along the position axis. And two, we're not dealing with a literal hill. We're dealing with a voltage map, not a elevation map. And the distinction between electric field being zero and voltage zero is usually pushed home at this one right here. Okay, remember this is our special y direction on the horizontal axis. So here, downhill is like so, in the negative y direction. Here, downhill is like so, in the positive y direction, or up. Positive y direction, up. Positive y direction, negative y direction. And then way out here we get an electric field of basically zero. But I want to focus in on this midpoint over here. At that location, the voltage is equal to zero. But the electric field is up. It's non-zero. Okay, because there is a slope there, and since there is a changing voltage, there's a different voltage from position to position, then we can say that there is going to be some electric field, because the electric field points, quote, downhill. I'm going to draw one more potential map now, and this one more is just going to be some random voltage map. Okay, it's gonna go up like so. It's gonna have a plateau up here, and it's gonna curve like so. That looks nice. On this voltage map, voltage versus, let's do X this time. There's many points where V is equal to zero. Okay, where is V equal to zero? V is equal to zero here, here, and here. There's also points where the electric field is equal to zero. And that'll be wherever there is no downhill, wherever the slope is zero. That'll include here, and it will include this entire plateau. This happens a lot with conductors, because inside of a conductor, the electric field is zero throughout the entire thing. Therefore, it's at a constant voltage throughout the entire thing. So it might be worth saying that right there, that's the voltage of our conductor. All right. So I wanted to clarify that distinction between high voltage and low voltage. In our other locations, we've got electric field pointing downhill, electric field pointing downhill, and electric field pointing downhill. There we go. Whole bunch of voltage maps, all considering the voltage values. Okay, so that's what you consider first. What are the voltage values? And it really helps to draw it out so you can visualize them. Once you know the voltage values, you can think about what the voltage slope is. Once you have information about the voltage's slope, you can know information about the electric field in the region. And once you know information about the electric field in the region, you can find the force, electric, that would be applied to some test charge. That would be some test charge multiplied by the electric field in the region. So we're going to go over these graphs one more time. Okay. I'm going to put in here a purple positive charge. And it's just going to be a positive test charge. Okay. So if I put it here, then it's going to be pushed in the same direction as the electric field, because F is equal to Q times E. If the electric field is to the left and Q is positive, then the result is still going to be to the left. Similarly, at that location it'll be in the same direction, and way out here the forces keep on getting smaller and smaller, depending on where we put the charge. Whereas if we put the charge on the other side, it would be pushed to the right, or barely pushed at all, way out in the far away from the charge. This shouldn't be too surprising. Because we know that if we put a positive charge near another positive charge, it should be repelled. And that's what I'm seeing with all of these purple arrows. In contrast, and once I do this, it'll be officially way too many arrows. What if I put a negative charge in the region? Well, if I put a negative charge in the region, such as here, it's not going to be pushed in the same direction as a positive charge. It'll be pushed in the opposite direction as a positive charge. Okay. Same thing over here. If you put a negative charge there, it's not going to be pushed away from the positive charge. It's going to be pushed back towards the positive charge. Okay. And the closer it is to that positive charge, the stronger force it's going to feel. All right. In this situation, we can do the same idea, but I'm just going to do for a negative test charge. If I put a negative test charge here, it's going to be pushed away. If I put it here, it's still going to be pushed away, but weaker. Over here, it's going to be pushed away, but now away is to the right. And if I put it way over here, it could be so far away that we can't really read how strong the force is. So effectively zero. All right. Next one. This one I'm going to handle with a positive charge. So I'm going to have we need a new color. Let's make it a light blue. Yeah, that'll do. A blue positive charge that I can put anywhere I want. So if I put it here, and we just have a little positive charges being put in there, it's going to be pushed in the same direction as the electric field. If we put it here, it's going to be pushed stronger because of the stronger electric field. If we put the charge here, then we get F is equal to 0. No electric field, no force. Okay. And all the way down the line, we end up with electric fields and forces in the same direction. Now, they aren't the same in value, though, because the value for the electric force will be equal to whatever that charge is. Okay? So it could be the charge of a proton, 1.6 times 10 to the negative 19 coulombs. Or it could be a 1 nanocoulomb charge. Okay? That's still a positive charge. And it will experience a force in the same direction as the electric field, but the force will be scaled with the strength of the charge. Next. Same thing, but now I'm going to put a negative charge in here. If I put a negative test charge in here, it's going to be pushed in the opposite direction as the electric field, opposite direction as the electric field, opposite direction as the electric field. Out here, opposite direction as the electric field. Way out here, the force will be basically 0. Here, opposite direction as the electric field, and the like. The only thing I'm going to note here is if I put a charge here, and there's no electric field in that region, then the force on whatever charge I put here, whether it's positive or negative, the force will be 0 because the electric field is 0 at that location. All right. And that's the sequence. Visualize the values, visualize the slope. That tells you about the electric field, and it'll tell you about the direction of the force. But when you consider the direction of the force, be careful, because the charge could be positive or negative. All of that was for these 3 slides. Okay. Let's consider a new distribution of charge. No longer thinking about point charges. Here I'm wanting to think about something more numerical, because the electric field inside of a capacitor is a simple equation. What makes it so simple is it has no spatial dependence. Okay? It depends on the charge density, and it depends on the permittivity in the region, but it doesn't vary from position to position. It's the same electric field throughout this entire region between the plates. No spatial dependence. So when I say that the electric field is equal to the negative slope of the voltage in the region, okay, and this looks like it's in a y-hat situation instead of an x-hat situation, then I can determine the voltage difference for a situation like this, but only if I know the distance between the plates. solve this for delta V, and I'm going to do the magnitude of the whole thing. I'm not going to worry about directionality, just although I know that the positive plate will be at the higher voltage and the negative plate will be at the lower voltage. This can be rearranged so that the difference in voltage across my capacitor will be equal to the electric field inside that capacitor multiplied by the distance between the plates, so delta Y. The electric field, well, we already know that from up here, charge density divided by the permittivity in the region. And the delta Y from one side to the other is D. So that is the voltage across a capacitor. And that is where this came from. That's how I could calculate what I would expect it to be. Now, you'd also need to have a device that can measure charge density. That's a little difficult. Usually, you measure the voltage, not the charge density, because the voltage is far easier to read, to measure. The distance between the plates, on the other hand, that's something that could definitely be done, though. So, you can use a voltmeter and directly measure the voltage across the two plates. That's what the circle V is. Or you can calculate, if you somehow have the more difficult to find information of the charge density and the distance between the plates. I'm going to skip this slide and go on to the slide. What does this mean in a circuit? Well, here's an example of my circuit. Now, I made this slide coming up on 7 or 8 years ago. It's been a while. I think this is one of the first slides I ever made for when I started teaching. So I'm not too happy with it. Over here, I tried to draw a battery. And you may have been able to picture a battery as being like this. Okay, and it has some positive side and it has some negative side to it. And we can take some wire and we can attach the positive side to what's going to turn out to be our positive plate of the parallel plate capacitor. And we could have another wire go from the negative side of the battery to what is about to be the negative side of the parallel plate capacitor. What's with these two lines then? Those two lines are supposed to signify big and small. There's the big side and the small side. But if it's a bigger battery, many times we'll draw the big small multiple times. So that instead of drawing the battery out every single time to look like a physical battery, we can say, here's my battery, here's my wire, here's my capacitor, and here's the wire going back. Boom. And I can know a lot about the voltage across each of these. For one, we know that the wire is made out of some conductor. You know, like copper. When you have copper, and we can say that the electric field inside of a conductor is going to be 0. Now, copper is not a perfect conductor, but it is a very good conductor. It's good enough that we usually don't have to worry about its conductivity, resistivity, how good of a conductor it is, unless we have a very, very large quantity of it. So if I have a wire that is inches long, meters long, maybe even 100 feet long, then I would not worry about its resistance. But if I have a wire like the ones that go from one city to another, and those really high wires that you can see going like over hills and from like Los Banos to Gilroy, those ones, those extend for kilometers and kilometers and miles. Those ones I would be concerned about them not being the perfect conductors, and I would talk about a voltage across those. But for our little handheld circuit here, I'm going to say that the difference in voltage across a wire is going to be equal to 0. Difference in voltage across a short wire is going to be basically 0. It's not equal to, but it's basically 0. There's also some voltage across the battery. Voltage across the battery is, if you have a standard double or triple A, that's going to be a 1.5 volt battery. Okay, maybe you've seen some 9 volt batteries, 6 volt batteries, 12 or 24 volt batteries, like the ones in a car. Or maybe a variable power supply that can supply different voltages. Okay, so there's lots of values that the voltage across the battery could be. But in this situation, the voltage across the battery and the voltage across the capacitor are going to be the same. And here's why. When I start measuring across everything, I can measure from location A to location B, from location B to location C, from location C to location D, and from D back to A. That'd be a closed loop. So the difference in voltage in our closed loop would be, for example, the difference in voltage from A to A, which is 0. Okay, because A and A have the same voltage at them. Therefore, no voltage difference. But A to A has a process to it. There's your difference in voltage from A to B. There's your difference in voltage from B to C. Your difference in voltage from C to D. And lastly, your difference in voltage from D to A. All the ones that are wires, I'm going to cancel out. So B to C, 0. D to A, 0. So 0 is equal to voltage from A to B is the voltage across the battery. And C to D is the voltage across the capacitor. Therefore, these two must be equal in magnitude. For example, from A to B, that'd be a positive difference in voltage. Conversely, measuring from B to A would be a negative difference in voltage. High to low or low to high. In the same way, from C to D would be a drop in voltage, so negative delta V, whereas from D to C would be a positive difference in voltage. Okay. Because C and B are at the same high voltage, and A and D are at the same low voltage. This whole thing is called Kirchhoff's loop law. Okay. Difference in voltage around a closed loop or over a closed loop is zero. Kirchhoff always has a junction law, but we'll talk about that one when we get to current next week. Okay. So the voltage across the battery and the capacitor in this simple circuit adds to zero. They're equal and opposite. What does this have to do with the charge on the capacitor? Now, in this slide, I just flat out tell you that the capacitance, by definition, is the charge per volume. Okay. Sorry, not charge volume, the charge per voltage. Sorry about that. So that would be specifically the voltage across that capacitor. That's a definition answer. Here's another way of defining capacitance. I can say that the electric field across a capacitor is equal to the charge density divided by the permittivity in that region. And charge density is equal to the charge divided by the area of the individual plate. So that means that I can rewrite the electric field as the charge on the plate divided by the area of the plate and the permittivity in the region. I also know from up here that the difference in voltage across the capacitor is equal to the electric field across the capacitor multiplied by the distance across said capacitor. Plugging in this value for E, VC, this is Q, D over A permittivity. V is an external effect, okay? Someone applied a voltage across the capacitor and as a result charged it up. All the residuals though, D over the area and permittivity, those are related to what the capacitor is made of. Each plate has a specific area. You got the area of the plates. Those plates are some distance, separated by some distance. And for permittivity, you can put stuff between the two sides of the capacitor to change the permittivity in the region. And there's a slide on that later. But here's the thing. This red statement is not the capacitance, because a large area should lead to a large capacitance. So this is not equal to the capacitance, it's equal to 1 over the capacitance. I call this C equals A permittivity over D. The capacitor design equation. Because it focuses on the things you need to design a capacitor. How big it is, how much it's spaced out, and are you putting anything special between the two plates? That's it. Looking at this equation that I've now mixed up a few ways, this turns into voltage across a capacitor is equal to the charge on the capacitor divided by the capacitance. Boom. Just as I wrote there. And I can rearrange this in solve it for capacitance. Capacitance is equal to charge on the capacitor divided by the voltage across the said capacitor. Okay. And we could go back through the whole thing and get back to the capacitor design equation that way as well. This page sends you off to Wikipedia, because there's a Wikipedia page that lists dielectric constants. So if you go to Wikipedia and look up dielectric constants, you'll get a page that talks about these different materials you can put in the middle of a capacitor. And they can be used to make the capacitor hold more charge. Most values are somewhat small, between 1 and 100, but in some cases they have dielectric constants that can be in the thousands. The dielectric constant is actually this kappa. The dielectric constant. Someone thought that it was the same thing as the Coulomb's constant, and it is not. It is a property of a material, and it's something where you'd have to be told what it is, or you'd have to find it experimentally. So that'll be different for all sorts of different materials. But the key to the dielectrics is it makes it so that the capacitor can hold more charge. Okay. I'm not interested in going into more about dielectrics, because if I do, then I'll start talking about really cool crystals that do have different dielectric values in different directions. We don't want to talk about that. We want to stay focused on these capacitors. Okay. Because we don't always just have one capacitor in a circuit. Sometimes there's two. Sometimes there's three. Sometimes there's more. This is a situation with two capacitors in the circuit. One battery, two capacitors. They are connected in a way that they have a shared wire on one side, and they have another shared wire on the other side. As such, they have two common wires, okay, with a junction. There's a junction. There's a junction that goes off to other stuff in the circuit. In this case, a battery. We could have more things connected with these common wires, such as a third capacitor. But we're just going to focus on a two capacitor circuit, and then we'll extrapolate to a third one later. I'm going to redraw this sideways. Battery, capacitor, and capacitor. Looking at this circuit, I see loops in a bunch of different ways. I see a loop here that says that the voltage across the battery and the voltage across the first capacitor must be equal in value. I see another loop here that says the voltage across the first capacitor and the voltage across the second capacitor must be equal in magnitude. And there's a third loop I could look at all the way around the outside that says that the voltage across the battery and the voltage across the second capacitor must be the same. In other words, the voltage across the battery is equal to the voltage across the first capacitor, and it's also equal to the voltage across the second capacitor. Next, what about the charge? The charge came from the positive to there, or it went from the same location to here. There's a choice. There's a choice because you have some total charge coming from the battery. And it's split, so that some charge goes to the first one, some charge goes to the second one. No charge is leaking out, no charge is going out to the environment, therefore, that's what the charge does. It comes from the battery to the capacitor. I need one more equation. My one more equation is going to be that V is equal to Q over C equation, but I'm going to write it differently. I'm going to write it instead as Q equals VC. The charge is equal to the voltage multiplied by the capacitance. I do this because I have a good charge equation down here, and I can replace each Q with V times C. There's a second reason why this equation is helpful. This equation is helpful because it can give you a little mnemonic for anyone that remembers the QVC home shopping network. If you don't remember it, not as helpful. But for those of you that have been stuck in basic cable with nothing good to watch, you probably ended up watching QVC for longer than you'd like. So there's that. So for each Q, I'm going to replace it with the appropriate VC. So Q total was from the battery. So that was voltage across the battery multiplied by the total capacitance. That's the total capacitance of the circuit. Next, Q1, voltage 1, capacitance 1. Q2, voltage 2, capacitance 2. I then remind myself, all those voltages are the same. So I divide by the voltage, and that cancels out all of the voltages, leaving me with the total capacitance of this circuit will be equal to the capacitor 1 plus capacitor 2. And if I do put that third one in there, it can be the third one in there as well, if it's there. This configuration is called the circuits being in parallel. As such, this is the equivalent capacitance for capacitors in parallel. Capacitance for capacitors in parallel. Good. We're coming up on the 1 hour mark. So it's one of the longer lectures we've had so far, but we should be finishing before the hour and 15-minute mark. There's another way of getting this equation. The other way of getting this equation is by looking at the capacitor design equation. Okay, how are we going to do that? Well, Same setup. We have a battery. It's going off to a capacitor. And it's also going off to a second capacitor. I'm going to take each wire that is common and shrink it so that it's no longer a big long wire, but instead connects here. And the other wire, instead of connecting big and long like that, is going to connect there. So I'm just shrinking the wires. When I do that, I'm also going to bring the capacitors a little closer together. So I got my first capacitor with a connection here and a connection there. And capacitor 2. Now it really does look like one equivalent capacitor. Okay, by just slamming it together like that. How did we slam it together? Well, really, this is a 3D object. That what we've done is we've increased the area of the capacitor. Because there is some area 1 for that plate, and area 2 for that plate. And if we put them all together, we get that the area total is equal to area 1 plus area 2. This is the type of information that we also have in our capacitor design equation. As such, it's worth noting that I'm going to say that the distance between the plates, d, is the same the whole way across, just for simplicity. Okay. And that the permittivity is the same inside both materials. All right. So I'd like this to look more like the capacitor design equation. C is equal to A E over D. Well, that's what I can do. I can take both sides of the equation, multiply it by the permittivity, and divide it by the distance between the plates, and distribute that through. That gives me area total times the permittivity divided by the distance between the plates equals the area 1 permittivity over the distance between the plates plus area 2 permittivity divided by the distance between the plates. This first term looks just like the total capacitance equation. This next term is the capacitor 1 equation. And this last term is the capacitor 2 equation. And therefore we get the total capacitance in a parallel circuit. So 2 derivations done. I think the second one's actually much easier than the first one, but they teach different concepts. That's the idea. That's not the only way that the capacitors could be arranged. Okay. And those 2 derivations I went through, they're also on these 2 pages. We can also have capacitors set up in series. For series, there's only a single common wire for the entire series. But the key to that single wire is that there is no junction. With no junction, there's no offshoots. There's no going off to here, going off to there, etc. It's just a singular path. And we're going to reduce it down to being a singular path but with a single capacitor in it. And the result is going to look a little different. I'll do it over here. Battery. Actually, I'll do battery, capacitor 1, capacitor 2. Now in this loop, there's 3 elements in the loop. One loop, 3 elements. Therefore, the voltage across the battery plus the voltage across the first capacitor plus the voltage across the second capacitor must add to 0. And the way I have this arranged, that's going to be positive, and these are both going to be negative. Next. There's also going to be charge moving around in the circuit. But if I move in here, I realize that I have a gap here and a gap here. So any charge that builds up on this plate here had to come from this plate over here, because it wasn't going to jump the gap. It just can't do that with the capacitor. This plate becomes positively charged. This plate becomes negatively charged. And it's all because electrons went over there. Electrons went over there, making one side positive, the other side negative, of equal value. So Q1 and Q2 are equal in value. And so is Q of the source. So Q from the battery is equal to Q1 is equal to Q2. I'm going to replace the voltage equations. I'm going to replace the voltage equations with V is equal to Q over C. So I get VB turns into charge, charge from the battery, divided by the total capacitance. And the negatives, I'm going to move to the other side. It's equal to charge across 1, capacitance of 1. Charge across 2, capacitance of 2. All of those charges are the same, so I can take the whole thing, divide it by Q, and all of these charges will cancel out, leaving me with 1 over the total capacitance in series is equal to 1 over C1 plus 1 over C2. And I want to be very careful about something here. Okay? When you add these together, what if C1 was equal to 6 farads? That's the unit for capacitance. And C2 was equal to 3 farad. What would the total add to be? There's always a couple students in the class that would say that it's 9. It's not. 1 over C series is equal to 1 over 6 farad plus 1 over 3 farad, which is the same as being 1/6 plus 2/6, which equals 3/6, or 1/2. At this point, a lot of people say, oh, the answer must be 1/2. So, no, it's not. Because we're not looking for what the inverse of the capacitance is. We're looking for what the capacitance in series is. So it'd be 2 farads. Okay? So be careful. You have to create a common denominator to add these things together. And once you've added them together, you still have to flip it over. You still have to take the reciprocal. 5 minutes left. Let's do another derivation. Actually, I'm going to show you a really fast way to do the math for 1/6 and a third. This is 1/6 of a circle. This is 1/3 of a circle. So this whole thing here must be half of a circle. In that way, a sixth plus a third is equal to a half. When you can learn your math by just thinking about pi, it makes it so much easier. I'm about to do another derivation. The first one used the Kirchhoff laws. The second one's going to use the capacitor design equation. But instead of zooming in and looking at the charge motion, I'm going to reduce the size of this wire. And I'm going to reduce it until we end up with the middle part all smashed together. So that our total capacitance there was related to this total distance. That total distance is going to be D1 plus D2. All right. Now for this one, I can try to get it to look like the capacitor design equation. C equals A permittivity over D. Kind of. Because the D is already in a numerator. So instead, I'm not going to make it look like the capacitor design equation. Instead, I'm going to make it look like the inverse of the capacitor design equation, which would be D over area permittivity. So I'm going to take my distance equation. I'm going to divide both sides by the area and the permittivity, which gives me D total over area permittivity is equal to D1 over area permittivity and D2 over area permittivity. As expected, I'm getting inverse relationships. 1 over the total capacitance in series is equal to 1 over the capacitance of the first one plus 1 over the capacitance of the second one. If there were more, then I'd add on more in series, as need be. That is our derivation. And I've got 1 minute left till my hour and 15-minute mark. Okay. With that 1 more minute, I want to note identifying series and parallel. In the orange circle here, I've got a common wire on the left and a common wire on the right. But there's a junction here and a junction here. Since there's a junction on your common wires, that means this must be parallel. In parallel, we can add the capacitors together directly and get 4 farad. Now 1 farad is a lot of capacity, so 4 farad is a very large capacitor. Usually the capacitors are much smaller than this. Once I simplified that, these two have a common line between them. They are in series. Being in series, I have to do the inverse equation. 1 over C equivalent will be equal to 1 over 4 plus 1 over 4, which will be equal to 2 over 4, which is equal to 1/2. And then don't forget to flip the result. C equivalent is equal to 2 farad, as we see right there. Okay. Check out this and the rest of this in the notes. See if the reductions it does from one step to the next make sense. There's one silly thing about this, though. When we reduce this entire giant combo circuit from 6 different capacitors on the left all the way down to a single capacitor over here on the right, it reduces down to a 6 farad capacitor, which is ridiculous, because we could have just used this 6 farad capacitor. Okay, so it might not be the most practical circuit, but it's a good way of visualizing, can you identify 2 capacitors in parallel? Can you identify 2 capacitors in series? And end up with reducing an entire circuit down to a single capacitor. That's what we're going to be practicing on our first lecture for week 4. Capacitors, and then we're going to introduce resistors after that. That's it for week 3, lecture B. Voltages, connecting those to electric fields, and applying both of those ideas to capacitors. There we have it.